Good morning, guys. Good morning. Good morning, Dia. All right, so let's wait for your friends to join up. Good morning. Good morning, guys. All right. So, guys, today we are going to continue our discussion on the carbohydrates. This is our lesson number 2 on the same. All right, and what are we going to discuss today is the reactions of sugars. Okay, this is what we are going to talk about. In the previous session, we had discussed basically all the important names and all the important structures of all the monosaccharide as well as the disaccharides. So today we are going to move onwards with that, right? So guys, you already know about me. I am Jagriti Sharma, CSIR-UGC NET Educator on Unacademy. And yes guys, I have been teaching for last 4 years, and I'm a plus verified educator. Also, I have cracked CSI net exam, All India rank 11, and GATE 2000, GATE rank All India level for 240. Okay. So, yes, just in case if you didn't know about me. Alright. Now, before moving onwards, let me just remind you once again what's going on in the Plus platform. So, I have already launched a course from June 2000. Yes, Ria, isn't it? So yes, June 2022 already started. Okay, 22 June 2022. Yes, that is it. So yes, guys, the course has started on organic and inorganic chemistry, and the topic that I have started is organic reagents. For those who are interested in joining, you can just visit my profile and see the course page. Also see the active courses because there are other active courses too. Okay, so see the upcoming and the ongoing courses which are there in the profile, and all the plus students, please enroll properly. All right, so if you want to join an Academy Plus, you can do so. Also, guys, you can join me on Telegram, and for the Telegram, the name of the group is CSIR-NET 2022, right? You can join up on Telegram as well for regular notifications and the class notes and everything. Okay. Also, what is going on academy special class basically. So every day 6 p.m. we are doing a battle of pole, which is basically free practice session. All right, and the topic that is going on right now is stereochemistry. So we are doing this practice battle of poles on stereochemistry. Followed by this, we are going to have a new topic, chemical bonding. That is free practice on chemical bonding. If you are joining for the first time, you can use the code Jagriti S. Okay. Yes. All right, guys. So now we are going to continue our discussion. Yes. First thing that we are going to study today is the OSA zone reactions. So everyone, you have studied this in your BSc and MSc. OSA zone reaction, OSA zone formation. Yes. Osazone formation of ketoses and hexoses. So it's a very simple reaction, guys. Let's see what is it. So when you are using phenylhydrazine on the molecule of glucose, so how do we remember glucose? We remember glucose by this code 2122. That is the OH. The first OH is on the right hand side. We call the right hand side 2 and we call left hand side 1. So we remember it like this: 2, 1, 2, 2. Okay? 2, 1, 2, 2. This is how we remember the glucose. Alright? So we are going to move onwards now. Very, very simple. Just remember 2, 1, 2, 2. Okay. So if you are using one molecule of, or let's say three molecules of phenylhydrazine, we get this molecule in particular. Alright. So what has happened in this molecule, guys? The first OH group and your CHO aldehyde group, both of them have converted into the hydrazone form, isn't it? They have converted into hydrazone, and this is known as the OSA zone. So OSAZONE, OSA zone. All right. So which molecules are going to, there is a question like this, which sugars are going to give you the same OSA zone, right? Yes. So the ones which are having the same structure on these two carbons, they are going to give you OSA zone, the same OSA zone. So basically, let's look at fructose molecule. You have CH2OH. This is a ketose, right? You have an aldose over here, aldohexose. That is your glucose. You have a ketohexose over here. In this way, this is a ketohexose. All right. So this one is fructose. Now guys, the rest of the molecule is just like glucose, isn't it? Only the first two carbons are different. And the first two carbons are going to be converted into the hydrazone formation, right? So that is why we say that glucose and fructose will give you the same OSA zone. Is there any other molecule which will give the same OSA zone as glucose and fructose? Can I say mannose? Yes or no? Absolutely. Yes. Why? Because mannose is a C2 epimer of glucose. So, yes. If we draw the structure of mannose, it is 1122, isn't it? Mannose is 1122 like this. So once again, the rest of the molecule is the same, and it is also going to give you the same OSA zone because CHO and the CHOH, they will be converted into the hydrazone. So glucose, fructose and mannose, all of them will give us the same OSA zone. Will give us the same OSA zone. Okay. Now there is one more question regarding the OSA zone, guys. That is, if you are only converting the two groups, the CHO and the CHOH, if you are only converting these two groups into the hydrazone, why do you require three molecules of phenylhydrazine? Yes. Why 3 moles of phenylhydrazine are required? Yes. Yes, everyone. Why do you require 3 moles of phenylhydrazine? You are only converting the two of these groups into phenylhydrazine. Yeah, phenylhydrazone basically. Okay, so let's look at this. What is happening, guys? Let's see the mechanism. So, mechanism of osazone formation is something like this. Chalo. So first of all, guys, let's say we are starting with the glucose or the mannose. So glucose and the mannose, both of them are going to have this kind of a structure, CHOH, and the rest of the molecule is the same. So we are not going to consider it. Okay, it is going to be as it is. So the first molecule of phenylhydrazine is going to be occupied. It is going to be occupied in the formation of phenylhydrazone. So absolutely from the free end, it is going to connect and you have CH and OH over here. Okay, rest of the molecule as it is. Now what happens is a ketoenol tautomerism happens. Just like you have a ketoenol tautomerism, you are going to have the similar type of tautomerism. And what happens is there is a hydrogen over here, isn't it? This hydrogen on this carbon. This hydrogen is going to fall over here and you have this kind of a species. NH, one double bond on this side and the rest of the molecule as it is once again. So what is happening? You have done the ketoenol tautomerism. The hydrogen has shifted. Now you are doing one more type of change in the molecule. What is that? See, the change is going to be like this. You have taken, yes, this lone pair of nitrogen is going to take away this proton. The bond is going to fall over this carbon and this bond falls over here. So ultimately the bond breaks. Yes, so you are going to get the imine. Alright, so you are getting the imine out of here. One carbon carbon single bond, C double bond O. The rest of the molecule is as it is. And who has eliminated, guys? Aniline molecule has eliminated. Yes. इसको हम क्या बोलते हैं? Specifically we call this kind of a rearrangement as the Amadori rearrangement. Okay, we call this Amadori rearrangement. So first of all, I will use 1 mole, yeah, 1 molecule of phenylhydrazine to convert it into phenylhydrazone. Tautomerism follows. After the tautomerism, we are doing Amadori rearrangement, and here you see that you are getting the imine type of molecule. All right, there is a NH over here, imine type of molecule. So now you can directly say, I can use 2 moles of the phenylhydrazine to basically do this attack once again, but now you can use 2 moles, convert both of these groups and remove the groups over here. इन दोनों को remove करके you can just directly get the phenylhydrazone. Alright, or you call it the OSA zone, isn't it? You call it the OSA zone. Now there is one more question regarding the OSA zone, same groups. Okay, there is one more question regarding the OSA zone, that is why OSA zone formation takes place, why the OSA zone formation takes place only on the upper two carbons, only on the upper two carbons. मतलब कि when we are talking about osazone formation, why only the two carbons are involved? Why the other carbons are not involved? That is the question. Okay, why the other carbons are not involved? Because yes, because we can say that this system will be stable just like this. How? ये बहुत important है, guys. So let me just show it to you how it is going to be as it is stable. So there is this NH and pH, and here I'll write the NHPH below. This system is going to make a stable six-membered like intermediate. All right, stable six-membered intermediate या फिर six-membered product. Why is it stable? This is stable because of the hydrogen bonding. So hydrogen bonding gives you a six-membered ring, almost a ring. Okay? So this is one of the reason that the lower carbons will not be oxidized because this system is stable like this. As it is going to stay. No more oxidation. Alright? So it fails to undergo further reaction because of the stabilization of the OSA zone because of the hydrogen bonding. All right, very, very important this thing. Yes, hydrogen bonding, absolutely. So I think that OSA zone formation is clear to all of you. Why we are using 3 moles of hydrazine, that also clear. What is the mechanism, that is clear. And why OSA zone formation take place only on the upper two carbon, that is also clear. Yes, so we can move onwards. Right. So we can move onwards and we see simple synthesis reactions of carbohydrates, guys. So as it is a very simple and direct topic. So let's talk about the Kiliani-Fisher synthesis. Is it a very simple reaction, Kiliani-Fisher synthesis? Absolutely it is. Yes, Chetan, last concept once again. ये देखो चेतन यहाँ क्या बोला है? Why the osazone formation does not happen for the remaining OH groups? मतलब कि ये तो देखो intramolecular oxidation हो रहा है, isn't it? The molecule only had one aldehyde group, दूसरा तो CHOH था. So this CHOH is also getting converted into the carbonyl via tautomerism and Amadori rearrangement. Okay, so the same could happen for this carbon also. अब इसके पास में भी तो OH है. The same could happen over here and then over here and then over here. But why the lower carbons are not doing the osazone formation? Why is the reaction only stopping over here? Because the osazone formation of these two carbons are going to form a six-member ring like this due to hydrogen bonding. ठीक है? हाइड्रोजन बॉन्डिंग की वजह से स्टेबल है. तो और आगे वो नहीं होगा ऑक्सीडेशन. यस, नो ऑक्सीडेशन, नो osazone formation. Okay. Now let's talk about the Kiliani-Fisher synthesis, guys. It is also known as a step-up reaction. Yes. What's happening over here? Let's say we have taken arabinose. You remember the structure of arabinose? That was a aldopentose, isn't it? Yes. Aldopentose से start करते हैं arabinose से. So what was the structure of arabinose 122? Ribose में all of the OH were on the same side. Arabinose may one OH on the left, remaining two like this. So this is your arabinose molecule. D-arabinose. This start here. Okay. Now guys, if I am attacking cyanide on the free CHO, what is the characteristic reaction, guys? Cyanide को attack करवाते हैं, aldehyde पे क्या मिलता है? Cyanohydrin. Yes, you will get the cyanohydrin, isn't it? Yes. So the remaining OH जो जैसे था उसको वैसे लिखो. The remaining OH were as it is. When the cyanide is attacking, the double bond O becomes OH. So that OH we can keep either on the right hand side, okay, or that OH can also be kept on the left hand side in this way. Yes, two possibilities of the cyanohydrin. ओके अच्छा, ये ऐसे ऐसे कैसे रख देंगे गाइज हम इसको? कोई लॉजिक नहीं है इसके पीछे, ऐसे कैसे रख देंगे? लेफ्ट कर दिया, राइट कर दिया, ऐसे थोड़ी होता है. हाउ आर यू डूइंग इट? वी आर डूइंग दिस बिकॉज द साइनाइड, this carbonyl is a planar molecule. The cyanide could attack this phase of the carbonyl so that O minus goes on the right hand side, or the cyanide could attack from below so the OH minus goes on the left hand side. That is why we can write both of these possibilities. Okay, इसलिए हम ऐसे लिख सकते हैं that the OH can go on two different positions. Now what? Now we have the conversion of this cyanide group. हमें पता ही है that if we hydrolyze the cyanide, we'll get the acid. So we get the acid on hydrolysis. Alright. Now, what I'll do is I'll heat this molecule. On heating this molecule, it is going to eliminate minus H2O. Minus H2O from where? I can use this OH, this third OH group, to form the acetal. If I'm doing minus H2O, then at least I can get an ester over here. ऐसे करके. Alright, so it forms a lactone by the removal of water, and then I can finally reduce it with sodium amalgam. When I reduce this system with sodium amalgam, it gives me this molecule CHO and the rest of the same molecule. So what is this? 2122? Yes, are you able to see? This is glucose. This one. Good morning all. Okay. Yes, this is D-glucose. All right, very good. So guys, ये तो हो गया D-glucose, but let's say we are doing all the steps same over here. सारे steps same करें हैं. This part of the question is going to give you. All right, let's write CHO directly. What is this molecule which is synthesized? Yes. Is it 1122? Is it D-mannose? Absolutely, it is D-mannose. So the Kiliani-Fisher synthesis is, guys, very direct. Okay. First of all, you'll form the cyanohydrin, then you'll do the hydrolysis, acid mil jayega, then heat, get 1, 2, 3, 4, 5 gamma lactone, and then you reduce with sodium amalgam to get the D-glucose or the D-mannose. You have started with the D-arabinose. Okay, चलो बहुत सिंपल है. Okay, chalo guys, this was a very simple reaction. Now we move onwards and we are going to do degradation, because step up reaction you have seen, step down also you must see. ठीक है, so these are some example जब जहाँ से direct question आते हैं carbohydrates का. ठीक है, so let's do rough degradation. Okay. So what happens in the rough degradation? Let's say I'm starting with D-glucose. I will first convert the molecule. I react it with bromine water. Yes. अच्छा. Do you remember guys कि अलग अलग type के oxidation levels होते हैं? With bromine water, what will happen? Yes. And with nitric acid, what will happen? So nitric acid is going to do both the oxidation of the CHO and the CH2OH. And bromine water is only a mild oxidizing agent, so it is only going to oxidize the CHO into COOH. What do we call this molecule? इसको क्या बोलते हैं guys? Is it aldonic acid? Yes. ये क्या है? Aldonic acid. If this is your aldehyde, this is aldonic. So if this is D-glucose, is gluconic acid और नाइट्रिक एसिड ऑक्सीडेशन से क्या होता है? ग्लूकारिक एसिड. मतलब बोथ दी CHO and COOH, CH2OH will be oxidized. है ना? Very good. Now we convert this into a calcium salt, CaCO3 and heat. Whole twice calcium. So we are basically converting this into a carboxylate salt, alright, of the calcium, and now we are going to heat it 30% H2O2 and ferrous acetate. मतलब basically iron in the 2 plus oxidation state and 30% H2O2. What will happen? देखो decarboxylation happened. मतलब कि this CO whole twice, this is going to be removed. And the next carbon will be automatically oxidized. This one is automatically oxidized. So I am writing CHO, this molecule. According to nomenclature, gluconic acid is correct और aldonic acid. देखो ये aldohexose है. अब aldonic acid में तो ना all those acids which are forming from aldoses, that would be correct. लेकिन particularly glucose के लिए बना रहे हैं ना. Okay, so we can call it gluconic acid also. No, that's not wrong. Right. So D-glucose now converted into D-arabinose. Yes. Yes. ये देखो. So in the Kiliani fissure, we started from D-arabinose and we went to D-glucose and a mixture of D-mannose also. But here we break the D-glucose down to specifically give D-arabinose only. हो गया ना degradation step down reaction. Yes, it is a step down reaction that we are doing. Okay, so this whole thing is understood, yes or no? Tell me quickly. All right, अब देखो guys, we do something really important. Now we are going to discuss the change in the optical rotation of glucose. ठीक है? And what is so important about it? Let's understand the term nuta-rotation. What is nuta-rotation? Let's see. ठीक है? So let's say guys, I have one pure form of D-glucose. जैसे कि ये रहा. I have one pure form of D-glucose. Now you are going to tell me कौन सा D-glucose है, अल्फा या बीटा? The specific rotation of glucose is plus 112 degrees. Yes, it is the alpha form. So, alpha form, ये हो गया plus 112. If I am taking this in the pure form, तो ये plus 112 है. Similarly, if I take this form, this is the beta form, isn't it? All equatorial. Specific rotation of the beta form. So of the pure beta form it is going to be 18.7. मतलब कि 18.7 degrees is for the pure beta form. ठीक है. लेकिन क्या होता है when I am taking the solution. Okay. When I'm taking the solution of both of these, they are going to give me a specific rotation of the overall solution is always going to be plus 52.7 degree. So whenever you say कि हम glucose के लिए ले रहे हैं specific rotation, you will always say it is plus 52.7 at equilibrium. Why does this happen? Why does it happen, guys? ऐसा क्यों होता है? At equilibrium, why is this your specific rotation? Okay, because what happens is at equilibrium कुछ अल्फा है वो बीटा में चेंज हो जाता है and कुछ बीटा अल्फा में चेंज हो जाता है, right? So at equilibrium we have some percentages. We have 36% of the alpha form and 64% of the beta form. This is what you have at equilibrium. इक्विलिब्रियम के ऊपर ऐसा नहीं है कि इसका 50 इसका 50, नो. 36% of the alpha form and 64% of the beta form. This is what you are getting. Alright guys, अभी ना यहाँ पे क्वेश्चन आता है that why you will see that this is the more stable form, isn't it? All of these OH are on the equatorial position. इससे ज़्यादा और क्या चाहिए किसी मॉलिक्यूल को? That all the substituents are on the equatorial position. This is the most stable form beta. लेकिन इसका सिर्फ 64% है. Why not 100%, guys? Why not 100% beta form? Big question. Yes. क्यों नहीं होता 100% beta form? Although it is all in equatorial position, can we say that we have a reason for this? What is that? The reason is anomeric effect. What is anomeric effect, guys? Anomeric effect क्या होता है? Anomeric effect is basically an interaction. It is basically an interaction. That is कि कोई भी electronegative group है, keep that group on the axial position on the with respect to this hemiacetal carbon. Okay, मतलब कि same carbon जिससे oxygen connected है. Keep that group on the axial position. It will be more stable over there. Why? Anomeric effect है इसलिए 36% of alpha बन गया. Otherwise 0% of alpha would be there. Why? Because this is very stable beta form. But कुछ तो अल्फा में है कि इसलिए वो 36% आ गया है. What is the reason? Anomeric effect. So anomeric effect is basically the interaction of the non-bonding electron pair on the oxygen goes into the sigma star orbital of the carbon oxygen bond. ये देखो, this is the sigma star orbital. So sigma star of the carbon oxygen bond is absolutely empty. Is empty, और क्योंकि वो empty है इसीलिए the oxygen gives the electron density into this. हाँ तो दो, कोई बात नहीं, इसमें भी दे दो. Give it over here also, इसमें भी दे दो, इसमें भी दे दो. What is the problem? Why still axial position? Because in the axial position this overlap is the best, isn't it? Oxygen N to sigma star. So this N to sigma star transition is only possible if OH is axial. ठीक है? N to sigma star is only possible if the OH is axial, not in the equatorial position like this. उससे क्या होगा? Orbital interaction अच्छा नहीं होगा. Okay, so that is why we still have 36% of the alpha form even though beta is more stable. Now this is the mutarotation combination of D glucose. ऐसा जरूरी नहीं है all the sugars are going to give the exact combination, not necessarily. Let's see another example. Let's see alpha D mannose. तो guys अल्फा डी मैनोज के अंदर, अल्फा एंड बीटा डी मैनोज के अंदर so you tell me कि mannose is a C2 epimer of D-glucose, yes or no? Mannose is a C2 epimer of D-glucose. तो ये जो C2 position पे OH है ना, we have to keep it over here. And the rest of the molecule is as it is. So this is your alpha D mannose and in equilibrium with okay, in equilibrium with the beta D mannose. But what is the percentage? Is it still 36 and 64? Absolutely not. कोई जरूरी नहीं है कि यही percentage होगा. For the alpha D mannose, you have 69% at equilibrium. Alright, 69% this is, and beta D mannose के लिए only 31% at equilibrium. Okay, so these are based on different molecules. Sub molecules अलग अलग percentage देते हैं guys, but the term is still mutarotation. That is, while we are taking a solution, yes, while you're, even if you have taken a pure alpha D mannose form or pure beta D mannose form, जैसे ही solution में डालोगे equilibrium आ जाएगा. Okay, yes, so look at this. Look at this one guys, so high alpha. इतना ज्यादा अल्फा क्यों है? Yes, absolutely, the reason is the same, N2 sigma star interaction. Okay. Alright, correct, anomeric effect. So now we are going to see uh, more reactions. ये देखो, chemoselective reactions basically. What is chemoselectivity? that is which group is reacting. ठीक है? तो yes, let's see. Let's say we have D-glucose, because most of the reactions are done on D-glucose only. So that's why we are having this reaction, okay, in this way. Chalo. So let's say I have taken a bulky molecule. I have tertiary butyl diphenyl phenyl PL. Okay, all right, very bulky. And in the presence of AgNO3. Yes, what is this, guys? TBDPS. This is tertiary butyl and diphenyl phenyl group. All right. Yes, tertiary butyl diphenyl phenyl group, like this. SiCl. Now, what is going to be the product? Obviously, ये silicon ether बनाएगा. Yes, but where is that going to happen? It is going to form the silyl ether, but which OH is going to react? Can you tell? Yes, anyone? Anomeric position. Don't you think it's a little bit bulkier for that? ये रहा, यहाँ पे connect होगा. Okay, so no, here we are going to connect this onto this oxygen. However, what happens is, guys, when we say that anomeric position is more reactive, ये भी correct है. Anomeric position is more reactive. So what we are going to do is हम पहले anomeric position को cover कर देंगे. Alright, so this is, let's say, OH, OH and OH. So let's say we provide methyl iodide. So when I'm providing such a simple reagent, methyl iodide करके, where is it going to attack? It is going to form an ether on this oxygen, on the anomeric oxygen. तो ये बन जाएगा OCH3 over here. This is OCH3. Similarly, this carbon is protected first only. अब कर दो. Yes. So इतना बड़ा जो ये है protecting group OTBDPS, it is a very bulky protecting group. It is going to protect the primary alcohol, which is only one. All right. How do we remove it? How do we remove this group and bring back our molecule? Yes, we want to form this molecule once again. What we are going to do, we are going to provide a fluoride source. TBF दे दो, या फिर OH minus is also going to do, but yes, TBAF is more effective क्योंकि हमें पता है we only want to remove the silicon, and that is having a high affinity for the hard donors like this. So you can take the TBAF, that is the tetrabutyl ammonium fluoride. Okay, this was easy. Chalo, let's do more reaction. Now a particular type of question comes for your glucose, cyclic form of glucose basically. Let's say I have a ketone molecule and H plus, and I have benzaldehyde and H plus. So what is going to happen to this molecule in the presence of these two? ये क्या करेगा? Yes, every year, almost every second year, there is a question based on the protection of the diols. Yes, guys, so roughly telling you about this, your ketone and aldehyde are going to do the same thing. They are going to protect the diols. क्या करते हैं देखो ऐसे, they will form acetals. Acetals कैसे बनेंगे? Diol protection से. So the selectivity is which diol? 1,2 diol or 1,3 diol? So acetone will protect the 1,2 diol. It prefers to do so. Okay, and the aldehyde will once again prefer to protect the 1,3 diol. इसका reason क्या है guys? Reason है that when you are forming the six member ring will absolutely be there in the chair conformation. तो chair conformation बना ली, very good, but chair conformation stable भी होनी चाहिए. Yes, so this hydrogen is going to have less 1,3 diaxial interaction as compared to the possibility when the acetone would be there. तो acetone 1,3 diol को protect नहीं करता है, और actually it is not favored. Alright, it is not very favored. Alright, not favored. Why? Because if you are drawing the six-membered ring with two oxygens, one CH3 above, CH3 below. So CH3 is a bulky group as compared to this hydrogen over here. तो ये बिल्कुल फॉर्म नहीं करेगा because of greater 1,3 diaxial interactions, right? इसीलिए yes, because of the diaxial interactions, so what will happen? Aldehydes will favor the formation of 1,3 diol, and acetone will favor the formation of 1,2 diol. I hope it makes sense. चलो अभी रिंग पे अप्लाई करो. Where is the 1,2 diol that you have, and where is the 1,3 diol? 1,2 diol, guys, if the 1,2 diol has to form, it would be really good कि वो 1,2 diol cis हो, क्योंकि already guys 5-member ring बनेगा, because acetone is going to donate to the it's going to protect the 1,2 diol. It would not want to do that with a trans junction, so it will be better if you form the cis junction. कैसे करेंगे? You have to take this in the open chain form, because अभी यहाँ पे 1,2 diol cis is not present. ठीक है, so you take this into the open form. ठीक है, 2,1,2,2, you take this into the open form, and this has formed 6-member ring because we did the hemiacetal formation through this oxygen. अब ये small oxygen, ये देखो एक कार्बन नंबर लेस है यहाँ पे. Do it from this oxygen, 1 2 3 4, it gives you a 5-membered ring, CHOH. Okay, all right. So basically the last carbon is not chiral, but I'm just writing it in this way so that you understand कि ये एक possibility है. Here you can get the 1,2 diol. Okay, and also if you want to draw this ring in this way, वेरी इजी इट इज। ये देखो, ये वाला जो कार्बन है हैज वन हाइड्रोजन एंड वन ऑफ दीज टू ग्रुप्स, OH एंड OH, लाइक दिस। ये वाला कार्बन लेट्स से यहाँ आ गया है। ऑल राइट, देन वेयर इज दिस कार्बन? राइट ओवर हियर, OH is trans, this carbon is above, and let's say this is their hemiacetal carbon. ये वाला carbon hemiacetal carbon है, so I can keep the OH above or below depending, right? So ये देखो, these two could be protected and then these two could be protected. So the molecule is going to look like this after protection. Okay, मतलब कि क्या हुआ है? Basically what has happened, the two of the cis diols, cis 1,2 diol are converted into the protecting, are basically protected by the acetone in this way. ये possibility है when you are providing the acetone. You have to convert into 5-membered ring, then you are getting two of these 1,2 diol. लेकिन aldehyde के लिए we don't do that. Aldehyde is going to protect the 1,3 diol, and also it is not necessary, it will require a cis junction. तो इसलिए हम क्या करते हैं guys? Yes, we take the same molecule as it is. Where is the 1,3 diol? These two. These are the 1,3 diols. Okay. So try to form a ring from these. ये देखो. This is your oxygen. This is one more oxygen. There is a hydrogen above and a phenyl group below. You have tried to form one more ring. ये वही acetal ring है. Okay, but you have just drawn it in the chair conformation. Please see once. No strain, because the ring is like, the rings are big. Second thing is 1,3 diaxial interaction is also very less. Also what happens is, ये बन गया हमारा रिंग. अब देखो क्या है यहाँ पे, 1,3 diol present था पहले से. Trans junction is also favored. Trans is favored. ठीक है. In the first one trans was not favored, that is why we have to break the ring. और ring break करके open chain लिया. Open chain करके you form the 5-member ring. You have the furanose form over here, and this is stable in the pyranose form, right? So very important guys, this is that why the aldehydes are going to give you the 1,3 diol protection, लेकिन acetones होता है या फिर any other ketone, why that does not give you the 6-member ring. One last very important reaction of this category of carbohydrates is your HiO4 oxidation. वो भी देख लेते हैं. HiO4 oxidation. Yes, so what is happening? I want to break down a molecule. The question will be asked like this, कि how many number of, या how many moles of periodate या periodic acid is required for the oxidation. ठीक है. So ऐसे देखते हैं इसको guys. You are having these for OH group. In the presence of periodate IO4 minus, you will form, alright, you are going to form an intermediate in this way. अभी जो intermediate है guys, it is going to break down okay. Yes, two of your carbonyls plus IO3 minus. IO3 minus. This is what you're getting. So परआयोडेट ऑक्सीडेशन में हमने क्या किया है, वी हैव रिड्यूस्ड द परआयोडेट टू IO3 माइनस, एक ऑक्सीजन निकल गया, and here the bond cleavage is taking place also followed by oxidation. तो अगर मैं आपको एक simple example दूँ guys, let's say I am having CHO 2122 basically. One, two, three, four, five, and six. You are having CH2OH. अब देखो क्या करना है. You are using HiO4 and you are breaking down one by one. मतलब कि दो, देखो guys, you can break this bond from here which is in between two of the OH group, or you can also do the same when you are having one of them as CHO. अब ये CHO किस में convert होगा? The CHO is going to be converted into HCOOH, मतलब कि just one step ahead of what you already have. एक कट हुआ यहाँ से HCOH. Okay, very well. दूसरा वाला क्या बन जाएगा? CHO. Since it is CHOH, it is going to become CHO. फिर यहाँ से कट करो. You will get one more mole of the acid and this has become CHO. फिर यहाँ से कट करो. This will become CHO and one more molecule is added. And then what happens? This is CHO. एक बार फिर से break करेगा. Okay. एक बार और break करेगा guys. Finally what happens is, ये देखो, ये वाला let's say CHO था. So this bond has to break from over here. So if this bond is, if this carbon is converted into HCOH, right, this is going to be only converted into the aldehyde, isn't it? Only one step forward. तो डी ग्लूकोज के पर आयोडिक एसिड ऑक्सीडेशन से क्या मिलेगा? 5 moles of the formic acid okay, this one, 5 moles of the acid and only 1 mole of the aldehyde, right? So this is what you will get. Okay, so take a homework guys. ये आपका oxidation है. Take one more homework, that is, if I want to do the HiO4 oxidation of this molecule, let's say fructose, CH2OH, C double bond O, H, OH, HNOH, and one more HNOH, CH2OH. इस molecule में क्या product मिलेगा? HiO4. And how many moles of HiO4 are going to be required? Also, what is the product? Okay, so I'll do this in the next session. All right, chalo. All right, so now I'll see you in the plus session at 10:30 a.m. All right, guys. Bye, everyone. We'll see you very, very soon, everyone, guys. Bye bye.